Have you ever just looked around? Really looked at the screen you're on right now, the chair you're in, even yourself, and just wondered, what is all this stuff made of?
Well, it turns out the universe is kind of like a giant, super complex Lego set. And today, we're going to get our hands on those fundamental bricks, the smallest pieces of reality, atoms and molecules.
So, what if you could get your hands on the instruction manual for everything? The rule book that explains how it's all built and how it all fits together. Sounds like something out of a sci-fi movie, right? But it's not. It's chemistry. And understanding atoms and molecules, that is finding the instruction manual. Our story here starts a long, long time ago with a really simple idea. You see, this whole journey to figure out what matter is, it didn't start in some fancy high-tech lab. Nope. It started more than 2,500 years ago with a really simple but kind of profound thought. Imagine this. If you take something, anything, and keep cutting it in half and in half again, do you eventually hit a point where you just can't cut it anymore? And what's really cool is that this wasn't just happening in one place. This quest was global. Way back around 500 BC, an Indian philosopher named Maharishi Kanad was talking about paramanu, these tiny indivisible particles. Then, about 100 years later, over in Greece, you've got Democritus and Leucippus, and they coined the word we still use, atomos, which literally means uncuttable. Now, for centuries, this was just a cool idea, a philosophical concept. It wasn't until guys like Antoine Lavoisier came along that it started to become a real measurable science. Okay, so scientists are finally on board with this whole atom thing. Great. But that just leads to the next big question, right? How do they actually work? Do they just bounce around randomly, smashing into each other? Well, it turns out not at all. They follow some really strict rules. In fact, there are two unbreakable laws that are basically the foundation of all chemistry. All right, rule number 1, the law of conservation of mass. You can think of this as chemistry's ultimate no-free lunch policy. It's super simple but incredibly powerful. In any chemical reaction, you can't just create matter out of thin air, and you can't make it vanish into nothing. The universe is like a perfect accountant. Every single atom you have at the start has to be there at the end. They just get rearranged into new partnerships. Let's make this super practical. Imagine we've got a sealed glass flask sitting on a super sensitive scale. Inside, there are two different liquids, kept separate. We note the weight. Then, we tilt the flask, the liquids mix, and poof, a chemical reaction happens. Maybe it fizzes up, maybe it changes color. Once it's all done, we look at the scale again. And guess what? The mass is exactly the same. To the tiniest fraction of a gram. Nothing was lost, nothing was gained. The atoms just swapped partners. Okay, on to rule number 2. This one is called the law of constant proportions. Now, this one's less about the total amount of stuff and more about the recipe. It basically says that any pure chemical compound, let's say water, will always have the same elements in the exact same proportions by mass. It doesn't matter if you get your water from a glacier, a river, or a lab in Cleveland. Water is water. Its recipe is totally non-negotiable. And yeah, water is the perfect example here. Take any sample of pure water. For every 1 gram of hydrogen in there, you are always going to find 8 grams of oxygen. Always, without fail. That 1:8 ratio by mass, that's like water's chemical fingerprint. It's a totally fixed recipe. And if you mess with that recipe, well, you just don't have water anymore. It's something else. So we've got this ancient idea of atoms, right? And now we have these two ironclad laws that seem to govern them. But all the pieces are still scattered. Enter John Dalton. He was an English school teacher who finally took all these ideas and put them together into one single coherent theory. He basically created the first real scientific blueprint for the atom. And Dalton's theory was it was beautiful, so simple and elegant. He said, look, all matter is made of these tiny, indivisible particles called atoms. And hey, these atoms can't be created or destroyed. Boom, that perfectly explains that first law, the law of conservation of mass. Then he said, atoms combine in simple whole number ratios to make compounds. And there you go. That's the why behind our second rule, the law of constant proportions. He handed scientists this incredibly powerful new way to think about the world. But, and this is what I love about science, it's always updating itself. Dalton's blueprint was absolutely revolutionary, but as we looked closer, we started to see a few cracks. Turns out, atoms aren't actually uncuttable. They're made of even smaller things like protons, neutrons, and electrons.
And we also found that not all atoms of the same element are identical. Some have slightly different masses. We call those isotopes now. But even with these corrections, Dalton's core ideas were so spot on that they became the absolute foundation for all of modern chemistry.
All right, so now we have this growing list of different kinds of atoms, elements. And scientists, being practical people, realized they needed a better way to talk about them. I mean, you can't be writing out hydrogen and oxygen every single time. They needed a shorthand, like a universal alphabet for matter.
Now, a lot of the symbols are pretty straightforward, right? H for hydrogen, O for oxygen, makes sense. But then you get some weird ones. Ever wonder why iron is Fe or why sodium is Na? It seems totally random until you dig into the history. Fe comes from the Latin word ferrum. Sodium's Na is from natrium. And potassium, K, is from kalium. It's kind of this cool little nod to the classical roots of science. Now, you could imagine, with scientists all over the world discovering new elements, things could have gotten really chaotic fast. To stop that from happening, there's an official group that keeps everything in order. They're called the International Union of Pure and Applied Chemistry, or IUPAC for short. Think of them as the guardians of this universal language. They make sure that when a chemist in Tokyo writes H2O, it means the exact same thing to a chemist in Toronto. Okay, so we've got our atomic alphabet. Now we can start writing words, which is basically what molecules are. A molecule is just two or more atoms stuck together. But how do we know the right recipe? How do we know how to spell these chemical words? For instance, how would we write the formula for something like aluminum oxide?
Well, the secret ingredient here is something called valency. And the best way to think about valency is to imagine that every atom has a certain number of hands it can use to link up with other atoms. Some atoms might have one hand, some have two, some have three. This number, its valency, is what determines exactly how it can combine with other elements. And chemists have this super handy trick for figuring this out. It's called the crossover rule. You just write down the symbols for your elements, then you take the valency number from each one, and you cross it over to become the little subscript number for the other element. So, for aluminum oxide, aluminum has a valency of 3, oxygen's is 2. You cross them over, and you get Al2O3. It's a fantastic little shortcut to get the right recipe every time. Okay, so we can write the recipes now, that's great, but chemists still have this massive problem. Atoms are just impossibly small. I mean, a single drop of water has more atoms in it than there are stars in our entire galaxy. Think about that. So how on earth can you work with them? You can't count them one by one. You need some way to connect that invisible world of atoms to the world we can actually see and measure, the world of grams on a scale. The solution is a concept that is pure genius. It's called the mole. And no, not the fuzzy animal that digs in your yard. In chemistry, a mole is just a number. It's a word for a quantity, just like a dozen means 12 of something. A mole just means a specific and very, very large number of atoms or molecules. It is the perfect bridge between counting and weighing. So, what is this magic number? Get ready for it. It's called Avogadro's number, and it is just staggeringly huge. It's 6.022 times 10 to the 23rd. That's a 6 with 23 zeros after it. It's so big that if you had a mole of donuts, they would cover the entire surface of the Earth in a layer 5 miles deep. Yeah, it's a totally mind-bending number, but for the teeny tiny world of atoms, it's actually a really practical, workable amount. So when you boil it all down, don't let the big number scare you. The mole is just the chemist's dozen. That's it. It's one word for one very specific, very big number. And it makes it way easier to talk about and measure out huge quantities of atoms. And this is where the real genius of the mole comes in. This is the magic part. The mass of 1 mole of any substance, measured in grams, is numerically equal to its atomic mass. So, carbon's atomic mass is about 12. That means 1 mole of carbon atoms weighs, you guessed it, exactly 12 grams. All of a sudden, you don't have to count a sextillion atoms. You just have to weigh out 12 grams of carbon. The mole is that perfect bridge from the invisible atomic world to the very real lab bench. I mean, when you just take a second to step back, it's an absolutely incredible story, isn't it? We went from an ancient philosophical guess, just an idea about tiny particles, to discovering the fundamental rules of how they play together. Then we created a universal language to talk about them, and finally, we figured out a clever way to count them by the sextillions just by using a scale. It's amazing. And really, that brings us right here, to the future. So if these atoms are the Lego bricks and we have the instruction manual, it just makes you wonder, right? What are we going to build next? What incredible new materials, new medicines, new technologies are just waiting for us to snap them together? When you're working with the building blocks of the universe, the possibilities are, well, literally endless.